Alright, so I'm going to be working some examples on spherical coordinates. So spherical coordinates are a lot like polar coordinates, okay, in that we're measuring the radius from the origin. We're measuring the radius from the origin, except now instead of r, we're going to call it rho. So rho is just think of it as the distance from the origin. It's the radius, except now we're talking about in 3D. Okay, so in 3D though, we don't just have theta. Okay, we have theta and this phi. Phi is the angle from the z-axis. Okay, so this is a little bit weird because a lot of people would imagine that it would be measured starting in the xy plane going up, but no, it's measured from the positive z-axis to whatever angle we're interested in. Okay, so the formulas for these might seem a little bit complicated, but it's not that bad. So for example, z equals rho cosine phi. So here, if this is phi, the height, z, if I draw this straight over to the z coordinate, this height right here, that's just rho cosine of phi, right? That's this distance right here. That's this angle right here. Okay, so these other ones, it's also not hard to see. I'm not going to walk through them, but just for a quick example, right, we can convert this equation from spherical coordinates into regular x, y, and z coordinates. Okay, so here if I distribute this, I have rho squared sine squared phi sine squared theta plus rho squared cosine squared phi equals 9. Okay, so this looks like rho squared sine, rho sine phi sine theta all squared plus rho cosine phi squared equals 9. But what do we know about this? This right here, this is just y. Right, so this is going to be y squared plus, this is z, right? That's exactly what z is. This is z squared equals 9. Okay. Now we can also go the other way around. So just like in polar coordinates, we had r equals x squared plus y squared. In spherical coordinates, we have rho squared equals x squared plus y squared plus z squared. So, it's just the 3D analog. Okay, so I'm going to use that here, right? So I have x squared plus y squared plus z squared. So that gives me rho squared minus 2, and then what is x? X is rho sine phi cosine theta. So this is 2 rho sine phi cosine theta equals 0. I can simplify this a little bit. I'll move this to the other side. So I have rho squared equals sine phi, that's 2 rho sine phi cosine theta. And then if I cancel rho on both sides, then I have rho equals 2 sine phi cosine theta. Okay, so this is just a quick example on converting from spherical coordinates to rectangular coordinates, Cartesian coordinates, and vice versa. Okay, but what do these actually mean? So here, in each of these pictures, we imagine what if each of these variables was held constant. So in this case, rho is constant. Okay, in the sphere, rho is constant, right? So these are all of the points with a constant distance from the origin, right? That's just going to form a sphere. Okay, theta, right? So theta is the angle from the positive x-axis right here. Okay, so if that's constant, right, any vector is going to lie in this plane. It's going to have an angle of theta with respect to the x-axis, but I can, it can be any vector I want as long as it's in this plane, right? It's still going to have the same angle with respect to the x-axis. So it's going to describe a plane. Notice that's not going to describe the other half of the plane because then theta would be different. Okay, and if phi is constant, right, so phi is this angle here, right, the angle from the z-axis. Right, so here I can pick any theta, right, it's rotated all the way around the x and y axis, so that's any theta. And then here I can pick any value of r, right, so that's any radius. So it's going to be all of the points of any radius and any angle with respect to the xy axis as long as it has a fixed angle with respect to the z-axis. Okay, and then z is larger than pi, or pi over 2. It's going to be a cone facing down. If phi was equal to pi, it would just be the xy axis. Okay, so let's do an example. So evaluate x squared dv, where E is bounded by the xz plane. Okay, so the first thing we do is let's just convert the integrand, the thing we're integrating, to spherical coordinates. So x was equal to rho, I think it was sine phi cosine theta. I'm going to scroll up and double check. Yes. Okay, now whenever we change coordinates from, and then we square this, whenever we change coordinates from rectangular coordinates into spherical coordinates, we have to include the term rho squared sine phi d rho d phi d theta. Okay, so this is just like when we did polar coordinates, right? Whenever we changed it into r and theta, we had to include this r, dr, d theta. So this is the same thing. Whenever I go to spherical coordinates, I have to include this term right here. Okay, so this isn't that hard. I can simplify this a little bit, and this is equal to the triple integral of rho to the 4th sine cubed phi cosine theta squared d rho d phi d theta. Okay, now the hard part of these problems is actually coming up with the bounds. Okay, so here it describes we're integrating over the domain E, where E is bounded by the xz plane and the hemispheres, right? So this is a half sphere. Y equals square root this, and y equals this. Okay, so if I have, let's just look at this one first. If I have y equals square root 9 minus x squared minus z squared, then if I square both sides, I have y squared equals 9 minus x squared minus z squared. And then I move these to the other side, and I have x squared plus y squared plus z squared equals 9. Actually, let me write this as 3 squared. No. I guess it doesn't matter. So x squared plus y squared plus z squared, we know that that's equal to rho squared equals 3 squared. So this is just the surface, rho equals 3. Okay, so this is the sphere, rho equals 3, bounded on one side by the xz plane. So it's going to be kind of a half sphere. Right, so if this is the y, z, and I have x kind of along this way, right, this is the sphere kind of like this. So it's kind of it's the sphere on this half of the plane with a radius of 3. Okay, so if I do the exact same thing for this equation, right, y equals square root 16 minus x squared minus z squared, I do all the exact same steps and I get rho equals 4. So that's going to be the same thing except a little bit bigger, like this. And now I have rho equals 4. So the region it's describing is kind of this region right in here. Alright, so now I need to figure out what are my two angles. Okay, so let me imagine what this would look like if I was looking straight down. Okay, so I know on looking from the side, it's going to look like this, kind of like a half circle. And then if I was looking straight down, right, so we're looking straight down, this is going to be, this is going to be x, this is going to be y. And we know that it's bounded by the xz plane, so it's going to be like this. So z is sticking straight up out. Right, so this is the xz plane, and this is the region we're interested in. So remember phi, let's do first with respect to phi. So phi is measured from the vertical z-axis, right? So it starts off here at at phi equals 0, vertical, and then to describe the whole region, we have to sweep out from phi equals 0, right? We have to do this angle, we have to do all of these angles until we get to the other side. So this means that phi is going to go from 0 all the way out over to pi. Right, so that kind of sweeps out this region, and I'm going to redraw this. So here, and we had our two semicircles. So here we start off with phi equals 0 along the positive z-axis, and then we're kind of sweeping out along here, right, as phi gets bigger, right, until we get to the other end of our domain, which is down here. Okay, so here we see that it goes from 0 all the way around to pi. We know that the radius, it's going to describe this region here. So the minimum radius at each of these angles is 3, and the maximum radius is 4. So we have 3 is less than or equal to rho, less than or equal to 4. And what about theta? So theta, I'm going to look over here. So this is the top view of my object. Okay, so z is sticking straight out of the board. So theta is measured from the positive x-axis, right? So that's going to be this here, going around this way. So it's going to start at theta equals 0, right, at the positive x-axis. And to describe this whole region, we have to go all the way around. Right, we have to go around to here, to theta equals pi. So we're going to have the same bound. We start at 0, And then we sweep around until we get to pi. So this gives us the integral. Integral from, let's see, I did theta on the outside, 0 to pi. Integral from 0 to pi again. Integral from 3 to 4 of rho to the 4th sine cubed phi cosine cubed theta d rho d phi d theta. Okay, so I can simplify this a little bit. Notice here that rho, or this is a separable function, meaning that it's a product of terms involving rho, terms involving phi, and terms involving theta, right? They're all multiplied together. I don't have an addition of any of these terms. Okay, so what I'm going to do is first I'm going to factor out sine cubed phi cosine cubed theta, right? These, rho doesn't depend on these, or these don't depend on rho. So they're, as far as rho is concerned, they're constant, so I can pull them out of this integral, and I get integral from 0 to pi, integral 0 to pi, sine cubed phi cosine cubed theta, 3 to 4, rho to the 4th, d rho, d phi, d theta. Now, this right here, this term right here, it doesn't depend on theta or phi at all, right? It's a constant as far as theta and phi are concerned. So I can pull it out of those integrals as well. So this becomes integral 3 to 4, rho to the 4th, d rho, multiplied by, from 0 to pi, 0 to pi, sine cubed phi cosine, that shouldn't be cosine cubed, that should be cosine squared. Cosine squared theta, d phi, d theta. Okay, and I can do the exact same trick, and what this is going to give me is 3 to 4, rho to the 4th, d rho, integral from 0 to pi, sine cubed phi, d phi, integral from 0 to pi, cosine squared theta, d theta. Okay, so this is the product of each of these multiplied together. And this is what typically happens when I have a separable function like I do here, right? Where I can write it as a product of terms involving each of these different variables. Okay, so for example, if I had something like sine of phi plus theta, this wouldn't be possible. I wouldn't be able to separate it out like this. Okay. So I'm going to go ahead and work this out. There's nothing really special about working this out. It's just working out 3 different integrals. So let's copy that down. Okay, so the first of these integrals so integral from 3 to 4, rho to the 4th, d rho, that's rho to the 5th over 5 from 3 to 4. That's 4 to the 5 over 5 minus 3 to the 5 over 5. 10, 24 minus, what is that? It's 81 times 3. 81 times 3 is 243. 5, and that's just okay. And then integral of sine cubed. D phi from 0 to pi. So this is basic Cal 2. I write this as 1 minus cosine squared phi sine phi d phi. And then I use a u sub and I set u equals cosine phi. So du negative sine phi d phi. So then this becomes the integral of 1 minus u squared, actually negative and negative. So then this becomes minus cosine of 0 is 1, cosine of pi is negative 1 du. I can flip the bounds if I get rid of the negative. So this becomes from negative 1 to 1. And that's going to be 1 minus u cubed over 3 from negative 1 to 1. So it's going to be u, which I have 1 minus 1/3 minus 1 minus 1 cubed over 3. So this is, let's see, so it's 1 minus minus, that's plus, that's 2. And then, let's see, so this is going to be minus 1/3, minus minus, that's positive 1/3. So that's minus 2/3. So it's going to be 4/3. Right, that's 6 minus 2, yeah, 4/3. Okay, and then for the final one, integral of cosine squared theta. D theta equals, so I write this as integral from 0 to pi of 1/2 plus cosine of 2 theta over 2 d theta, and we integrate, so we get 1 over 2 theta. Integral of cosine is sine 2 theta over 4 from 0 to pi. So first term I get pi over 2 plus sine of 2 pi is 0. And then if I plug 0 into either of them, I get pi over 2. So my final result, this is equal to 781 over 5 times 4/3 times pi over 2. 781 is not divisible by 3. The 2's can cancel. 2. So for a final answer of, let's see, I'm going to have 2, 6, carry the 1, and 5 pi over 15. All right, next example. So this was one that I thought I made a mistake in on Monday, but it turns out that it was actually correct. I was just misinterpreting it. So here, when we're doing this triple integral, right, we're integrating this function over this three-dimensional region. So we are finding, it's not like we're finding a 3D volume, okay? We're evaluating the integral of this function over a 3D space. Okay, so that's not actually a, it's not actually finding a volume. Okay, so again, let's convert this to polar coordinates. So I do, this is going to be rho sine phi cosine theta times rho sine phi sine theta times cosine phi, and then we have to remember to multiply by rho squared sine phi d rho d phi d theta. So I simplify, and I get rho to the fifth sine cubed phi, and then cosine phi times cosine theta d rho d phi d theta. Okay, so this is a separable function, right? Like we saw before, right? It's a product of terms that don't involve each other, of the other variables. So now the only thing I need to do is figure out what are the bounds. So here E lies between the spheres rho equals 2 and rho equals 4. Above the cone, phi equals pi over 3. So if we remember up above, right, for a constant phi, we have it forms like a cone. So here, if I just look at this from, say, this is the x-axis and this is the z-axis, right, we have this cone here, and this angle is pi over 3. So this tells us right away that the region we're interested in, right, so phi, the angle from the vertical is going to start at 0 vertically, and we're interested in all the region from phi equals 0 to pi over 3. Right, so that's 0 less than pi less than pi over 3. Okay, but we're also told that rho goes from 0 to 2. Right, so that means it's going to look like this. Okay, so rho goes from 0 to 2, so that's from here to here. So that's also kind of immediate. Okay, but if we look at this from the top, so here's x and here's y, so we're looking straight down at the z-axis. This is going to look like this. Right, it's just going to look like a circle looking straight down. And this z, or phi going from 0 to pi over 3, that describes, right, this kind of slice that I described right here. On this diagram, that's going to be this portion right here. Okay, so here I need to rotate this all the way around. Okay, so here we need that theta needs to go from 0, right, it starts at the x-axis, and we rotate it all the way around to 2 pi. Okay. Now I could do this a slightly different way. I could say that phi goes from negative pi over 3 to pi over 3. If I did that, then the same diagram, then that represents going here, this whole region. If I do this, then I'm only going to need to rotate pi degrees, right? Because this half is also going to rotate, and we've covered our entire area. So either one works. I'm going to be doing this one when I do the actual integrals. They give the same answer. So here, remember I said I can write this as this is separable, so I can write this as the integral of rho to the fifth d rho sine cubed phi cosine phi d phi cosine theta d theta. And I know it's bound by 2 to the fourth. Phi is from 0 to pi over 3, and theta goes from 0 to pi. Okay, so if I start evaluating these integrals, I'll do theta first. Okay. This is so cosine theta d theta. So integral of cosine is negative sine. Hold on, this doesn't work. I just go to 2 pi. So this is sine theta from 0 to 2 pi, which is 0. Okay, so since this is 0 and we're multiplying all of these together, that tells us right away that this whole thing is going to be 0. Cool. So why does that make sense? Why would this be 0? So this is what stumped me up on Monday. I was a little confused on why would this be 0? I was thinking of this as like a volume, and it shouldn't be a 0 volume. But it's not a volume, we're just integrating this function. So let me point this out. If I was to do 1 over the volume of E times this integral of x, y, z, dx, dy, dz. What this represents is the average value of x times y times z, the average of this over that region. Okay, so this is actually fairly intuitive, right? Because here, the average x value over this region, since it's symmetric, is going to be 0. And the average y value is also going to be 0. So, since it's kind of symmetric like this, the average value of this function would be 0. So we would expect that the integral is going to be 0. But this is just a constant. So we would expect that this would be 0. So it kind of makes sense in that sort of geometric way.